In this unit, we're going to talk about problem solving, the theory and technology of building agents that can plan ahead to solve problems. In particular, we're talking about problem solving where the complexity of the problem comes from the idea that there are many states. As in this problem here, a navigation problem where there are many choices to start with, and the complexity comes from picking the right choice now and picking the right choice at the next intersection and the intersection after that, stringing together a sequence of actions. This is in contrast to the type of complexity shown in this picture, where the complexity comes from the partial observability, that we can't see through the fog where the possible paths are. We can't see the results of our actions, and even the actions themselves are not known. This type of complexity will be covered in a later unit. Here's an example of a problem. This is a route finding problem where we're given a start city, in this case Arad, and a destination, Bucharest, the capital of Romania, from which this is a corner of the map. And the problem then is to find a route from Arad to Bucharest. And the actions that the agent can execute are driving from one city to the next along one of the roads shown on the map. The question is there a solution that the agent can come up with given the knowledge shown here to the problem of driving from Arad to Bucharest? And the answer is no. There is no solution that the agent can come up with because Bucharest doesn't appear on the map, and so the agent doesn't know any actions that can arrive there. So let's give the agent a better chance. Now we've given the agent the full map of Romania. The start is in Arad, and the destination or goal is in Bucharest, and the agent is given the problem of coming up with a sequence of actions that will arrive at the destination. Now is it possible for the agent to solve this problem? And the answer is yes. There are many routes or steps or sequences of actions that will arrive at the destination. Here's one of them. Starting out in Arad, taking this step first, then this one, then this one, then this one, and then this one to arrive at the destination. So that would count as a solution to the problem. It's a sequence of actions chained together that are guaranteed to get us to the goal. Now let's formally define what a problem looks like. A problem can be broken down into a number of components. First, the initial state that the agent starts out with. In our route finding problem, the initial state was the agent being in the city of Arad. Next, a function, actions, that takes a state as input and returns a set of possible actions that the agent can execute when the agent is in this state. In some problems, the agent will have the same actions available in all states, and in other problems, they'll have different actions dependent on the state. In the route finding problem, the actions are dependent on the state. When we're in one city, we can take the routes to the neighboring cities, but we can't go to any other cities. Next, we have a function called result, which takes as input a state and an action and delivers as its output a new state. So for example, if the agent is in the city of Arad and takes, that would be the state, and takes the action of driving along route E671 towards Timisoara, then the result of applying that action in that state would be the new state where the agent is in the city of Timisoara. Next, we need a function called goal test, which takes a state and returns a Boolean value, true or false, telling us if this state is a goal or not. In the route finding problem, the only goal would be being in the destination city, the city of Bucharest, and all the other states would return false for the goal test. And finally, we need one more thing, which is a path cost function, which takes a path, a sequence of state, action, transitions, and returns a number, which is the cost of that path. Now, for most of the problems we'll deal with, we'll make the path cost function be additive so that the cost of a path is just the sum of the costs of the individual steps. And so we'll implement this path cost function in terms of a step cost function. The step cost function takes a state, an action, and the resulting state from that action, and returns a number n, which is the cost of that action. In the route finding example, the cost might be the number of miles traveled, or maybe the number of minutes it takes to get to that destination. Now let's see how the definition of a problem maps onto the route finding domain. First, the initial state we're given. Let's say we start off in Arad. And the goal test, let's say that the state of being in Bucharest is the only state that counts as a goal, and all other states are not goals. Now the set of all the states here is known as the state space, and we navigate the state space by applying actions. The actions are specific to each city, so when we're in Arad, there are 3 possible actions: to follow this road, this one, or this one. And as we follow them, we build paths or sequences of actions. So just being in Arad is the path of length 0, and now we could start exploring the space and add in this path of length 1, this path of length 1, and this path of length 1. We can add in another path here of length 2, another path here of length 2. Here's another path of length 2. Here's a path of length 3, another path of length 2, and so on. Now, at every point, we want to separate the state out into 3 parts. First, the ends of the paths, the farthest paths that have been explored, we call the frontier. And so the frontier in this case consists of these states that are the farthest out we've been explored. And then to the left of that in this diagram, we have the explored part of the state. And then off to the right, we have the unexplored. So let's write down those 3 components. We have the frontier, we have the unexplored region, and we have the explored region. One more thing, in this diagram, we've labeled the step cost of each action along the route. So the step cost of going between Nîmes and Iași would be 87, corresponding to a distance of 87 kilometers. And then the path cost is just the sum of the step costs. So the cost of the path of going from Arad to Oradea would be 71 plus 75. An algorithm that has traditionally been called uniform cost search, but could be called cheapest first search, is guaranteed to find the path with the cheapest total cost. Let's see how it works. We start out as before in the start state, and we pop that empty path off, move it from the frontier to explored, and then add in the paths out of that state. As before, there'll be 3 of those paths. And now, which path are we going to pick next in order to expand, according to the rules of cheapest first? Cheapest first says that we pick the path with the lowest total cost, and that would be this path. It has a cost of 75 compared to the cost of 118 and 140 for the other paths. So we get here, we take that path off the frontier, put it on the explored list, add in its neighbors, not going back to Arad, but adding in this new path, summing up the total cost of that path, 71 plus 75 is 146 for this path. And now the question is, which path gets expanded next? Of the 3 paths on the frontier, we have ones with cost of 146, 140, and 118, and that's the cheapest. So this one gets expanded. We take it off the frontier, move it to explored, add in its successors. In this case, it's only 1, and that has a path total of 229. Which path do we expand next? Well, we got 146, 140, and 229. So 140 is the lowest, take it off the frontier, put it on explored, add in this path with total cost 220, and this path with total cost 239. And now the question is, which path do we expand next? The answer is this one, 146. Put it on explored, but there's nothing to add because both of its neighbors have already been explored. Which path do we look at next? The answer is this one, 220 is less than 229 or 239. Take it off the frontier, put it on explored, add in two more paths and sum them up. So 220 plus 146 is 366, and 220 plus 97 is 317. Okay, and now notice that we're closing in on Bucharest. We've got two neighbors almost there, but neither of them is their turn yet. Instead, the cheapest path is this one over here. So move it to the explored list, add 70 to the path cost so far, and we get 299. Now the cheapest node is 239 here, so we expand finally into Bucharest at a cost of 460, and now the question is, are we done? Can we terminate the algorithm?
The answer is no. We're not done yet. We have reached a goal state. We put a path onto the frontier that reaches the goal, Bucharest, but we haven't popped that path off the frontier. And uniform cost search continues to search until we pop it off the frontier. We continue looking to see if there's a better path that also reaches the goal. So let's see, I forgot to say Fagaras is explored, so let's continue looking on the frontier. The cheapest now is here at 299. We'll expand that. We get a path of cost 374. Put that on the frontier. Now let's go again. Now the cheapest path is over here at 317. We'll mark that as explored and add two more paths. One here that's a worse path, so it gets dropped, and one path that also reaches the goal, and that has a total cost of 418. So that just shows it's a good thing we waited, a good thing we didn't stop when we found the first path to the goal, because now this second path found is actually cheaper than the first path found. But we're not going to stop here because we still haven't popped off a path that reaches the goal. So we'll continue. What's next? Now the cheapest path on the frontier is here at 366. We expand that and we get paths that are worse paths to points we've already seen before. So nothing new goes on the frontier. Next, the cheapest path on the frontier is at 374. Again, expanding that leads nothing useful, only worse paths than we've seen before. And now finally, the cheapest path on the frontier is this 418 path to Bucharest. So we pop that off, and now we reach the goal, and now we stop. So even though we found the 460 path first, we don't stop there because there might be another path that also reaches the goal that's cheaper. We keep on going until we pop a path off of the frontier that reaches the goal, and that's why uniform cost search is guaranteed to find the cheapest path to the goal.
Let's try to understand a little better how uniform cost search works. We start at a start state, and then we start expanding out from there, looking at different paths. And what we end up doing is expanding in terms of contours, like on a topological map, where first we expand out to a certain distance, then to a farther distance, and then to a farther distance. Now, at some point, we meet up with the goal. Let's say the goal is here. Now, we found a path from the start to the goal. But notice that the search really wasn't directed at any way towards the goal. It was expanding out everywhere in the space. And depending on where the goal is, we should expect to have to explore half of the space on average before we find the goal. If the space is small, that can be fine. But when spaces are large, that won't get us to the goal fast enough. Unfortunately, there's really nothing we can do with what we know to do better than that. And so, if we want to improve, if we want to be able to find the goal faster, we're going to have to add more knowledge. The type of knowledge that's proven most useful in search is an estimate of the distance from the start state to the goal. So let's say we're dealing with a route finding problem, and we can move in any direction, up or down, right or left, and we'll take as our estimate the straight line distance between a state and a goal. And we'll try to use that estimate to find our way to the goal fastest. Now, an algorithm called greedy best first search does exactly that. It expands first the path that's closest to the goal according to the estimate. So what do the contours look like in this approach? Well, we start here and then we look at all the neighboring states, and the ones that appear to be closest to the goal we would expand first. So we'd start expanding like this, and like this, and like this, and like this. And that would lead us directly to the goal. So now, instead of exploring whole circles that go out everywhere in the search space, our search is directed towards the goal. In this case, it gets us immediately towards the goal, but that won't always be the case if there are obstacles along the way. Consider this search space. We have a start state and a goal, and there's an impassable barrier. Now, greedy best first search will start expanding out as before, trying to get towards the goal. And when it reaches the barrier, what will it do next? Well, it will try to increase along a path that's getting closer and closer to the goal. So it won't consider going back this way, which is farther from the goal. Rather, it will continue expanding out along these lines, which always get closer and closer to the goal, and eventually it will find its way towards the goal. So it does find a path, and it does it by expanding a small number of nodes, but it's willing to accept a path which is longer than other paths. Now, if we had explored in the other direction, we could have found a much simpler path, a much shorter path, by just hopping over the barrier and then going directly to the goal. But greedy best first search wouldn't have done that, because that would have involved getting to this point, which is this distance from the goal, and then considering states which were farther from the goal. What we would really like is an algorithm that combines the best parts of greedy search, which explores a small number of nodes in many cases, and uniform cost search, which is guaranteed to find the shortest path. We'll show how to do that next using an algorithm called the A-star algorithm. The answer is that we select this path first, the one from Erod to Sibio, because it has the smallest value, 393, of the sum f equals g plus h. A-star search works by always expanding the path that has a minimum value of the function f, which is defined as the sum of the g and h components. Now, the function g of a path is just the path cost, and the function h of a path is equal to the h value of the state, which is the final state of the path, which is equal to the estimated distance to the goal. Here's an example of how A-star works. Suppose we found this path through the state space to a state x, and we're trying to give a measure to the value of this path. The measure f is the sum of g, the path cost so far, and h, which is the estimated distance that the path will take to complete its path to the goal. Now, minimizing g helps us keep the path short, and minimizing h helps us keep focused on finding the goal. And the result is a search strategy that is the best possible in the sense that it finds the shortest length path while expanding the minimum number of paths possible. It could be called best estimated total path cost first, but the name A-star is traditional. Now let's go back to Romania and apply the A-star algorithm, and we're going to use a heuristic, which is a straight line distance between a state and the goal. The goal again is Bucharest, and so the distance from Bucharest to Bucharest is of course 0. And for all the other states, I've written in red the straight line distance, for example, straight across like that. Now, I should say that all the roads here I've drawn as straight lines, but actually roads are going to be curved to some degree, so the actual distance along the roads is going to be longer than the straight line distance. Now, we start out as usual. We'll start in a rod as a start state, and we'll expand out a rod, and so we'll add 3 paths. And the evaluation function, f, will be the sum of the path length, which is given in black, and the estimated distance, which is given in red. And so the path length from this path will be 140 plus 253, or 393. For this path, 75 plus 374, 449. And for this path, 118 plus 329, 447. And now the question is, out of all the paths that are on the frontier, which path will we expand next under the A-star algorithm? The answer is we expand this path next because its total, 413, is less than all the other ones on the frontier, although only slightly less than the 415 for this path. Let's go ahead and expand this node now. So we're going to add 3 paths. This one has a path cost of 291 and an estimated distance to the goal of 380 for a total of 671. This one has a path cost of 239 and an estimated distance of 176 for a total of 415. And the final one is 220 plus 193 equals 413. And now the question is, which state do we expand next? And the answer is that we expand this path at Pythagoras next because its F total, 415, is less than all the other paths in the frontier. So we expand this node, giving us 2 more paths, this one with an F value of 417, and this one with an F value of 526. And the question again, which path are we going to expand next? The answer is that we're not done yet, because the algorithm works by doing the goal test when we take a path off the frontier, not when we put a path on the frontier. Instead, we just continue in the normal way and choose the node on the frontier which has the lowest value, and that would be this one, the path through Udacity, with a total of 417. Now we expand Pythagoras, and we get a path that reaches the goal, and it has a path length of 450 and an estimated distance of 0 for a total F value of 450. And now the question is, what do we do next? So let's expand the node at Udacity. We have to go down this direction, up, but then we reach a path we've seen before. And we go in this direction. And now we reach Bucharest, which is the goal. And the H value is going to be 0 because we're at the goal, and the G value works out to 418. Now again, we don't stop here just because we put a path onto the frontier. Rather, we put it there, we don't apply the goal test next. Now we go back to the frontier, and it turns out that this 418 is the lowest cost path on the frontier. So now we pull it off, do the goal test, and now we've found our path to the goal, and it is in fact the shortest possible path. In this case, A-star was able to find the lowest cost path. Now the question, which you'll have to think about, because we haven't explained it yet, is whether A-star will always do this. Answer yes, if you think A-star will always find the shortest cost path. Or answer no, if you think it depends on the particular problem given. Or answer no, if you think it depends on the particular heuristic estimate function h. The answer is that it depends on the h function. A-star will find the lowest cost path if the h function for a state is less than the true cost of the path to the goal through that state. In other words, we want the h to never overestimate the distance to the goal. We also say that h is optimistic. Another way of stating that is h is admissible, meaning that it's admissible to use it to find the lowest cost path. So think of all of these as being the same way of stating the conditions under which A star finds the lowest cost path.